As hinted, there are multiple rotations needed to restore the tree balance for this exercise. However, in future assessment, you may not be told whether or not there will be multiple rotations needed, so you have to know how to judge. And watch out how I do the justification as I go over the solution with you. And part A, we're going to insert the following sequence of keys into the empty BST as before. So we're going to start with 50, and then 25, and then 10, and then 30, and then 5, 15, 27, and then 1, and 75, and then 60, and then 80, and then finally 55. So these are the internal nodes, and let's now draw the external nodes as well. And then we'll annotate the heights for the tree. 1, 2, and also don't forget this one here. And also over here, and also there's one over here, don't forget. Over here, over here, over here, over here, over here. Right, let me just make them solid quickly, so you can see more visual distinction between internal and also external nodes. And the natural question is, after all these insertions, is the resulting BST balanced? Well, to judge, we have to annotate the heights for every node. Let's start with the external. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0. And we're going to annotate the height for the internal nodes accordingly. Hopefully, you're proficient in doing that already. So 1 here, and then 2 here, 1 here, 3 here, 1 here, 2 here, and then 4 here. So 1 here, 2 here, 1 here, 3 here, and 5 over here, right? You can definitely compare your answers. Well, if you actually pause the video and actually did it already. Is a tree balanced? Well, we got to compare the heights of every pair of the left and right childs quickly. 0 and 0, 1 and 0, 0 and 0, 0 and 0, 0 and 0, 2 and 1, 1 and 0, 1 and 0, 0 and 0, 3 and 2, 2 and 1, 4 and 3. The difference between the heights of the two child nodes are simply just less than or equal to 1. So that definitely satisfies the height balance property. So yes, it will be checked over here. And the next part will be, we want to delete a node from the tree. And how do we do that? Well, we're going to do that in a moment. And let me just move this tree a little bit to the right over here. Okay, let me do that. Okay. And for this part over here, for the 0, okay, let me just fix that very quickly. And then it's going to be 0. So I can copy the tree for the deletion. Okay, let me now copy the tree. And we want to delete one node from there. Okay, over here. And which node do we want to delete? We want to delete 80 from the tree. Where is 80? 50, 80 larger than that. 75, 80 larger than that. And 80. That's the node we want to delete, right? That's the one. And this is like case number 2 for the binary search tree deletion, because you can see for 80, the node we want to delete, it simply got 2 external child nodes, right? But of course, you should really know how to handle case number 3, in which case you may have 1 internal child nodes, or maybe case number 4, it got 2 internal child nodes. Those are the cases you need to know how to handle from the earlier lecture. And for now, we're simply just going to delete the 80, right? We're simply just going to convert it into an internal nodes. External nodes, sorry, over here. And let's now update the balance. This will be 0. And over here, you can see this part over here, the maximum amount 2 and 0 is 2. 2 plus 1 will be 3. So this one doesn't need to be updated. So this one doesn't need to be updated either. However, is the tree now balanced? The answer is no, because if you look at this pair of child nodes heights over here, 2 and 0, the difference is larger than 1. So it violates the height balance property for sure. Before I do the annotation, let me just copy this tree, which can be useful when we do the rotation. Okay, that's that. Good. So what I will do is I'm going to highlight about the part that violates the property, height balance property. You can see this part over here, the difference is actually 2. This is where the violation comes from. And I'm just going to put over here, is it balanced? The answer is no, it is not balanced. Like that. And what we should do is we should really identify the first node. You can think about this is the child nodes of the node that's being removed. This is, you can think about it's either the left or right child of the 80 that's removed. That's exactly over here. And we want to start from this node and look at its ancestor path. Let me just go to over here. This part over here is the ancestor path. This part over here, right? Let me just make a note quickly over here. So this is the ancestor path. And we go along and we can see that this is the node that has first become unbalanced for sure, right? This node itself is actually balanced because it doesn't have any child nodes, but this one, it will be the first one. So what I will do is I'm going to circle that. This will be A. This part over here. This will be A. And what about B? B is going to be the taller child. So this node here, A, has 2 child nodes. This one here and this one here. The height is 2 versus 0. Apparently, the taller one should be this one. And again, we verified the mathematical property, which we didn't actually have to prove. The taller child node that we choose as B is not part of the ancestor path over here. Right? Again, we verified the mathematical property the second time. So over here, this 60 over here would be B. Let me see if I can just draw that a little bit smaller so I wouldn't cover the heights. That's kind of the best I can do anyway. All right, so this is B over here. What about C? And for the C, you can see we got actually either this node over here or this node over here. We have to choose the taller child, right? You can see there's 1 versus 0, so we have no choice. We must choose this one here, the taller one. So what I'll do is I'm going to choose this one over here for 55. This one should be the C node. And we also have to identify T1, T2, T3, T4. So I wouldn't do the conceptual reminder as I did before for insertion case, but now I assume you know how to do it already. But I can help you a bit over here. Let's just try to look at the structure of the tree. So A connected to B, B connected to C, and also we got a various different subtree. We got one subtree here, one subtree over here, one subtree over here, and one subtree over here. So this is T1, T2, T3, and also T4. Luckily, they're all external nodes. And we have to do, what kind of rotation do we have to do based on what we understood from the insertion case? They're all slanting to the left. That means we want to do a single rotation on the middle node. And what kind of rotation should we do? You want to somehow promote this node here to the root. So we're going this direction. So it should be a single right rotation on B. Right? That's something we did earlier. So for that, I'm not gonna waste your time. Let me just write it down over here. So we're actually going to do a single right rotation. Right? Let me just do that over here. So we're going to do right rotation on the B node. In this case, it's actually 60. Right? And of course, to go from A to B, we are trying to delete. I forgot to annotate it. Let me do it now. So we're trying to delete 80. All right, so how do we do it? We somehow want to restructure this part over here. So B will become the root, right? Think about what's the Inorder Traversal. It's going to be 55, 60, and 75. So what we're going to do is 55, 60, and 75. That's the conceptual sketch, right, that we had earlier. Let me now paste the diagram which I copied earlier. Awesome. So we can save lots of writing. I just need to do the following. Right? So let me wipe out this part of the tree. This part over here is going to be done from scratch again. Okay, so this part over here. Right, think about this is the part that we want to do rotation. So this entire subtree is going to be restructured. And the way we do it, I'm going to use a different color. How about I can just use blue. I think that's fine. What we want to have is we want to have used to have C, A, B, and C over here. We want to have C, B, and A. So what that will end up with is we're going to have the B 60 over here, and then we have 55 and also 75. And also we got external nodes over here. Right, I'm just trying to present this exercise in a slightly different way, assuming that you have already gained some proficiency from doing this kind of exercise for the insertion cases, right? Hopefully you have made that improvement already. Let me just annotate this very quickly, and then, oh, you know what? I think I also need to have copy this for later. It seems like we might need another rotation according to the hints, but let's see if that's really the case. So what I will do now is I'm going to first of all show to you this one over here is now B, and this one over here is C, and this one over here is A. Used to be C, B, and A, but now we got C, B, and A in this way, right? T1, T2, T3, T4, T1, T2, T3, T4, right? Everything's consistent. Is this balanced? Well, we want to ask this question always. The in-order traversal has been preserved, but we want to the search property has been preserved, but we want to see whether or not it's still balanced. That's the question. So I'm gonna have 0, 0, 0, 0, and then this will be 1. This will be 1 for the heights, and this one will be 2, and then maximum amount 4 and 2 will be 4, so this is still 5. However, is this balanced? Apparently not, because you can see that along the ancestor path, we actually talk about this particular external node, right? So this is really the ancestor path. So the ancestor, and since we did the rotation on the B, so you can think about we should really continue with the ancestor path over here. Okay, we should really continue with in this way over here. In that case, do we have any unbalanced node? Indeed, you can see the 4 and 2 over here, it is unbalanced. So let me just highlight it over here. So this part over here, you can see the difference is actually 2, meaning that this will be the first node that's actually unbalanced. This one will be, okay? So I think to really avoid confusion, I may just have to delete the annotation over here. But those you have already seen the correspondence, so that's okay. Because I'm gonna need to rename A, B, and C again, so I don't want you to get confused. So this part over here, okay? This is the first node that has become unbalanced, so this will be A. And how do we choose B and C accordingly as before? For B, taller child should be here, which is not part of the ancestor path. Again, we verify the mathematical property. This will be B over here. And I'm going to annotate that as B over here. And what about C? For C here, we want to choose the taller child of B. We got 3 versus 2, and we have no choice. We have to choose this one because they are not of equal heights. If they are of equal heights, then we have to choose the one that will make A, B, and C slant the same way, but it's not the case over here. So we're going to choose the taller child, which will be 10 over here. So this will be C. And again, we have the situation. We have to this time. Let me also help you understand exactly what's going on over here. The structure: A connect to B, B connect to C. What about the subtree structure? This one definitely deserves maybe some highlights over here. So what about T1? T1 will be the left subtree of C. this will be T1. Okay, and for T2, it will be the right subtree of C, which is 10. Right, this will be T2. T3 will be the right subtree of 25 over here. So that will be this part over here. This will be T3. And what about T4? T4 is going to be the entire right subtree of the node 50. Right? After annotation, hopefully it's much clearer about what's going on. So we got A, B, and C. And also we got, you can see this is one connection, and also one connection, and also one connection. You can definitely refer to the abstract diagram that we spoke about earlier, right? It's really consistent. We got A, B, and C, and over here we got T1, T2, T3, T4. And after the rotation, what do we expect to see? Well, I would suggest for this one here, I can just draw from scratch very quickly. What we should do is, we should really have, first of all, C, B, and A. C, B, and A. That's what we should have. So let me draw that from scratch. So we got C over here, and then B over here, and A over here. Right? Let me move that to the middle over here. Let me just make sure you understand that. So this will be C, and this will be B, and this one over here will be A. If you do the in-order traversal just for these, 10, 25, 50, sorted. So the search properties satisfied. And what we should do is, we should really have different subtree over here. So we got 1, 1, 1, and 1. This one here should be T1, right? Okay, very quickly. This one here should be T1. This one here should be T2. This one here should be T3. This one here should be T4. Okay, let me copy that quickly. Right, that's also what you should do. So 5, and then we got 1. And I will update the heights altogether quickly. This might be a very good way to actually illustrate how you should really do it in the actual assessment. And T2 will be 15 over here, and then we got this and this. And for T3 we got 30 over here, and then we got 27. And finally, we got T4, which will be 60, and then 55, 75. And I'll talk about what the rotation we actually did. I haven't annotated yet, but that's actually quite obvious. So what we actually did was some rotation, a single rotation. Let me just go over here. What we did was, this was because they're all slanting the same way, so only a single rotation on B is needed. They're all slanted to the left, so that's why a right rotation again will be needed, right? Like that. You can see from before A, B, and C slanting to the left, and here A, B, and C again slanting to the left. So the same kind of rotation need to happen to be the case. Right rotation on the B node, in this case it is 25, right? So that's why it becomes the root 25 over here. And let's now do the in-order traversal very quickly. 1, 5, 10, 15, 25, 27, 30, 50, 55, 60, 75. We got in-order traversal being sorted. So search property is maintained. Is it balanced? That's a final question to ask. If it is not balanced, that means we may actually have to do further rotation, but in this case should not be possible because the last rotation we did was already on the root, so it should not be needed, right? It's very important for you to see the running time at the end, but I will talk about it in just a moment. Let me now fill out heights. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0. This one should be 1, should be 2, should be 1, should be 3, and then this one should be 1, should be 2, and then 1 and 1, and this one should be 2, should be 3, and should be 4, right? If you try to compare, for example, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1 0, 2 1, 2 2, and 3 3. So we have no violation of the high balance property. So we're good. It is balanced. Check. And of course, on the other hand, the previous one was actually not checked, right? That's why we did second rotation. Let me talk about the running time to conclude. You can see that we started with this particular external node over here along its ancestor path. This is the starting point. After the first rotation, we actually started from the rotation in the root. You can think about, in general, you may start anywhere in the tree to start a rotation after the deletion. And every time you finish a rotation, the next point of possible rotation will be a level up, strictly up. So you're basically moving towards the root over here. And how many rotation will be needed? In that case, it's really corresponding to the heights of the tree. So what you can think about is, let me just do a further annotation over here quickly. So since we are starting from this particular external nodes over here, right? So this part over here is really bounded by the heights of the tree. The number of nodes that you have to perform the rotations is really bounded by the heights of the tree. So that's why we said the running time should be big O of H. And in this case, because the tree is actually balanced, it will be big O of log n. That's really the concluding remark I would like to make. So rotation is actually a very efficient way to restore the balance because you only take log n as the number of rotations needed after deletion. But for insertion, only a single rotation will be needed. I'll summarize about the running time for these two kinds of operation on BST at the end. I'll do that. Alrighty, so that's the full solution. I'll walk through about this exercise over here. Make sure you understand the details over here about all the remark, and it will be the most important for your learning of the skills we're describing over here about tree rotations by attempting the exercise on your own from scratch. So grab a piece of paper, pencil, eraser, and do the exercise.